All right, folks, here we go. Video number 3. Let's start by looking at ionic bonds. Just a quick review here of what makes them so unique. We got the great positive, negative. We got that attraction everywhere, but what happens if you move the crystal just slightly? And we are talking a trillionth of an inch here. If you move the crystal just a little bit, what happens? You go from attraction to repulsion, and we do what? We break. And that's why we say ionic compounds are very brittle. They're almost always solids at room temperature. They ain't flexible. And what do we say about the melting and boiling points? Because they stick together very, very, very strongly, those are going to be what? High temperatures. Because they stick together and have no movement, they are going to be insulators. They will not let electricity flow. But then they also do dissolve in water very well, which is a whole nother can of worms. There's all those numbers again. We don't need to look at those. Lattice energies. There was one question on the Quizlet that was similar to this. On the Quizlet, I think it was comparing the strength of that. Was it calcium and chlorine? I think it was calcium, wasn't it? And this is going to have a much higher lattice energy. That's going to be a much stronger bond, mostly because calcium +2, chlorine -1. Sodium is just +1. +2 is going to be stronger than +1. The attraction that would have. Okay, but that was from one of the, I think it was, I can't remember if it was the first ed puzzle or the second ed puzzle. I might have said Quizlet. Okay, let's talk about metallic bonds here. This is what happens when you get two metals, and it's been a while, but we did have this discussion a long time ago. When you've got a metal and another metal, they both have 1 or 2 or 3 valence electrons. It varies. We know it varies depending on the metal. But they are both hoping to get rid of, what do we say? Metals like to lose electrons. But if there's nobody there to take the electron, you can't just like throw it and let the wind take it. And so metallic bonds are unique in that when you put all the metals, say you put them all in a room together, M for metal down here, you put them all in a room together and they just let their electrons run free. Okay, this is classic bad parenting. When you were younger and you came up to the gym to go to a volleyball or a basketball game and your parents just said, okay, go hang out with your friends, meet me back here in the lobby after the game's over. And they just let you run around. They didn't worry about you because they knew you were somewhere in the building. Well, that's what metals are like. The weird thing about metals, and again, this makes them bad parents, they don't care if they take the same electron home. Your parents pretty much wanted to bring the same kid home, but metals, they don't care. Okay, they figure I had 1 valence electron, I had 2 valence electrons, that's all I really need. Okay, and so long story short here, what do we say? In a metallic bond, all the electrons have been delocalized, okay, and D means un, local means located, okay, so we are unlocated, which means the electrons can be anywhere. We don't know exactly where, all we know is that they are somewhere in the metal. delocalized. And so this is all the words here. Electrons are not held by one atom. They are free to move. They can run around through the whole substance. And then one of the words on the Quizlet is they call that the electron sea. It's really not a liquid, but they call it the electron sea. Okay. And so again, another way to say a metallic bond, the metals bond with each other and mix all of their valence electrons together. It becomes what we call the electron sea model. The electrons are not held by one particular atom. They are just everywhere. They are free to go everywhere. And because the electrons are free, or maybe we should say mobile, since the electrons can move, that's what makes metals such good. What do they do? What do they conduct? Lots of things conduct heat, but metals are special because they conduct heat, and that's the biggie. They conduct electricity. Alrighty. They conduct electricity and heat. Heat's not the important thing here. Picture I swiped from the book. Notice how they went blue. I think they're trying for the sea model there. You know, water is blue and stuff. But who does this electron belong to here? I'll color him in. Who does he belong to? We don't know. Who is he attracted to? Everybody. Is he attracted to every positive? It'd be pretty weak here, but he would even be attracted to that positive. Okay. Who does this electron belong to? We'll go yellow for him. Our friend old Yeller is back. Is he attracted there, there, there? And so we would have the same thing here. In this one, boy, he's attracted everywhere. He's attracted. And so what you got to consider here, this is what makes metallic bonds so great. The metals, because they've gotten rid of an electron, they've turned it loose, they're all positive. And so the metals themselves hate each other to some extent, but love, probably not the right word, but are they attracted to those loose electrons? And so these two up here, they're repelling, but what overcomes that? Are they attracted? Are they both pulling on this same electron? They're not attracted to each other, but they're attracted to that electron. Same thing here. This one is attracted to that electron. So in a sense, it's kind of a weird thing, but are all three of these metals hooked together? They're not hooked directly, but they're hooked indirectly because they're attracted to the electron. And so you would have that situation going on all over the place. Here, group 2 metals, well, we just got more electrons. So would there just be more, and would there be different attractions? The difference between this and an ionic bond, okay, the difference between a metallic and an ionic bond is that the metallic bond, we say, since those electrons are mobile, if we push on that metal, it doesn't really matter. You're not going to get them to go from, with the ionic, remember, it's either really strong attraction, or if you nudge it, it's going to go strong what? Repulsion. In a metal, we don't have to do that. We say the layers slide past each other. Okay? The metallic bond is in all directions and it's flexible. That gives us these words. We've had these in play since January. Malleable. What's that mean? The word you're looking for is mallet, and a mallet is a fancy word for MC hammer. Hammer time. What can we do if they're malleable? We can pound them into shapes, sheets. Ductile. Go to your biology there. What is a duct? Is that a tube? Okay. Ductile means we can draw them into wires. Stretch them, pull them into wires. Another picture out of a book. I like this one. The metal. Why is it a cation? It's a cation because it's letting its electrons run free. Okay. So the electron is gone. It's positive. The C, we've got everywhere. Electrons all over the place. They're just loose. Okay. And we've got that indirect linkage between the metals because of that electron in the middle. We've got the atomic hammer here. Bump them over, but does the blue, does the C, does it shift? And so do we still have that attraction in between here, all these negatives? Okay, there's our definitions. Malleable, hammered, ductile, wire. That was the wrong button. So long story short, what do you know about a metal? Are there a lot of liquids, metals? No. What's the melting point? Is that a high temp or a low temp? That's a high temp. Boiling, same deal. We don't boil a lot of metals. Those are high temperatures. Okay. Malleable, you already had that written down in your brain. Ductile. Okay. What's the fancy word for shiny? Come on now, starts with an L. Lustrous. Luster. Okay. And what do? They're a dual threat. They conduct both, and this is the important one, electricity and heat. But lots of things conduct heat, so that's a secondary. The electricity is the big one here. Alloys, we just don't have a lot of time here, but what is an alloy? Strict definition, it's a mixture of two or more elements. Now, most of the time we say, and people usually think that it's a mixture of two or more metals. Well, yeah, to some extent, that's probably more common. The most common alloy in the world, probably steel. And you know what the two main ingredients in steel are? You've already said the one, iron. Second one, carbon. Non-metal. Okay. Pure iron, strong, useful, yes. Not that flexible, can be a little brittle, and so we add some carbon to it, and that gives us better properties. Okay, that's why we would make alloys. We are hoping for new and improved. We're hoping for better properties. Alrighty. Properties such as maybe I can mix a cheap metal in there, and so will it just save me money? Maybe it'll be stronger than a pure element. Maybe I get rust resistance. Okay, there's all sorts of factors that they're looking for. Chemical properties, cost. Cost is always a factor, of course. Okay, strength. If it's stronger, then I can use less of it, which will make it lighter and cheaper. Rust is a huge problem for us. Another good example, just to throw out there, because I know you've heard of it, there's regular steel. We build our buildings, our cars, there's structural steel, and then there's what you have in your kitchen. Stainless steel. Now the name is not right. It's not great because it doesn't stain. Stainless steel doesn't rust. Very, 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 very slow rust. And rust is a stain to some extent. But stainless steel is expensive, so we don't build a lot of stuff out of it. But do we put it on our refrigerator, our dishwasher, our stove, our grill? Okay, we use it for stuff like that. Another alloy, okay, boys, when you go to buy a gold ring in 10 years, Do not buy a pure gold ring. It's too expensive, it's too soft. All gold we buy in the jewelry store, folks, is probably, depending on what you're going to spend, 60 to 75% gold. And then the rest, hopefully, we melt some silver in there. Silver makes it stronger, makes it a little cheaper. Pure gold, very soft and very expensive. So there's 3 simple alloys. There's hundreds of them out there. Well, here's another one. Sterling silver, also used in jewelry a lot. Not pure silver. Okay, we melt a little copper in there with it. Money, 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 money. And here, numbers, numbers, numbers. But you've heard of a lot of these, I'm sure. Brass, we've heard of brass. 2 main ingredients in brass, copper and zinc. Bronze, 3rd place in the Olympics. Copper and tin are the biggies. Little bit of zinc in there. And you that have had the metals, welding and stuff, there are lots of different kinds of steel or iron out there. Okay, there's different amounts that we add. Can you believe this? 10 karat gold, which is legal to sell in America, is less than half gold. 50%, 42% gold. Then we throw in some copper and some silver. Shotgun shells, that's weak. Stainless steel, these amounts vary also. If a magnet sticks to stainless steel, it's cheap stainless steel. That means these numbers are very high and these numbers are lower. There's your sterling silver for jewelry. There's a picture of all the pictures. We don't really need that. So that pretty much ends ionic and metallic talk. I'll throw a little something up about covalent here in a couple days. We're going to do a little bit of drawing and so forth with the covalent, and then we're going to kind of move on into what I would call chapter 9, where we talk about some equations and so forth.